Okay, so welcome back to another video. So here we have a following infinite sum construction that we'd like to find what the convergent value to that is. And we have that this is 1 divided by 1 to the 5th plus 1 divided by 2 to the 5th plus 3 to the 5th plus 1 divided by 1 to the 5th plus 2 to the 5th plus 3 to the 5th, so on and so forth. So you see how the construction goes. So this actually follows the third video of the similar formulation of the construction of that infinite sum. The other two, if you haven't seen, I'll leave that link in the description below. But for anybody that's seen those videos, I think you can kind of see where I'm going with this procedure. Although the way we start off this writing out this formula is actually it's a sum of 1 divided by of a specific sum of the fifth power of that. So we can actually start off with that. But it actually follows a different procedure than the other two that I did in the past. But it also comes with a bunch of, not really a bunch, but a couple formulas we'll be using. One of them you'll see is that we'll be using the digamma function. And you'll also see the reflection formula being utilized as well of the digamma reflection formula as well, including another problem known as Basel's problem. So this is just some things to just keep in mind. So nothing more that needs to be said, as it just follows with a lot of manipulation algebra, and then those functions / formulas we'll be utilizing as well. So let's actually just jump right in. So let's actually start with, of course, I'll call this capital L, and then we'll write this in the form that as mentioned. So this, of course, this is the infinite sum, starting with our index of n is equal to 1 of 1 divided by, and then under the denominator, we're going to have a partial sum that follows with each index. So this is going to start from k is equal to 1 all the way up to n of k to the 5th. And as you plug in those numbers and do the expansion, you see that it follows exactly just like that. So it actually comes with a nice form for the k to the 5th power. So as we see, we know ones for k squared and even k to the cube. So what about k to the 5th? It actually comes down to the following formula written as n squared divided, multiplied with n plus 1 quantity square, multiplied with 2n square, add this with 2n, and then subtract 1, and then all this being divided by 12. And if you'd like to verify this, of course, proof by induction always works. So with this, we can actually make that substitution back over here. And so with the flip the reciprocal, so we'll have that this is the infinite sum from n is equal 0, or n is equal 1, excuse me. Now let me first, just to make things neat, I'm gonna write the denominator first. So n squared, then n plus 1 square, and then 2n squared subtract, or plus 2n subtract 1, and then 12 on the numerator, just for the sake of symmetry. Now for 1, I can actually factor out a 12 as the constant, and then after this, we're gonna have 1 divided by this entire denominator, and then what that comes down to is that if we apply some partial fraction decomposition, we'll have that the series will be written as follows. So we have 4 divided by 2n squared, add this with 2n subtract 1, then subtract 1 divided by n squared, and then subtract 1 divided by n plus 1, and then quantity square. So nicely, we can see that 1 divided by n squared, taking into account with this series of the infinite sum, we already know what that's going to converge to. But let's actually apply some linearity for 1, and we're going to split this into 3 different sums. So after applying some linearity, so we'll have 48. Then we have the infinite sum starting from n is equal 1. First is going to be 1 divided by 2n squared subtract 2n, or plus, I keep getting that mixed up, plus 2n, and then subtract 1. Then we're going to have subtract 12, and multiply with the infinite sum, n is equal to 1 of 1 divided by n squared. Then we're going to subtract this with 12 divided by the infinite sum, starting at n is equal to 1 of 1 divided by n plus 1, and then quantity square. So we already know what this is going to converge to, so let's substitute that value back into there. And then once we get to here, we'll notice that we can actually do a little bit of manipulation with the index over here. So first, we notice that if we start at n is equal to 0, so that would have to mean we have 1 divided by 0 plus 1, 1, and to the quantity square. But that means that if I start at the 0 term, then I have to subtract that back. Well, then, and afterwards distribute that, and that'll become a positive. So that means this is actually another way to rewrite the Riemann zeta function at n is equal to 2, the Basel's problem, and we know that's the Basel's problem too. So after all this, we're going to have the following. So this is going to stay the same, just like this. So 1 divided by 2n squared plus 2n subtract 1. Then next is going to be subtract 12, then multiply by the Riemann zeta of 2. I'll just leave that as the zeta function for now before we get to the pi squared divided by 6, once we get to the end of, combining everything together. Then next is, again, the Riemann zeta function again, but then we have to put in the take into account the n equals 0 term. So 2, and then that will change that to a positive with that negative, so that'll be plus 12. And so this is what we have so far. So we're actually, there's one last thing to do, and that is, of course, just to calculate what this sum is equal to. So I'm actually going to call this S, and then from there, we're actually going to find what that value of S is going to equal to. So notice that S is going to equal to this infinite sum that I just said, so that means we have to figure out what that is. 2n squared plus 2n and then subtract 1. And so what I'll do is let's actually take account to the n equals 0 term. So if that's the case, then I have to subtract one of the terms out. So in other words, we'll have that this is going to equal to 1 and then add this with the same infinite series like above, except this is going to start at n is equal to 0 of the same series, just like this. Now let's actually, what I'm going to do here is I'm actually going to factor out a 1/2. So 1 plus and then 1/2. Then with the infinite sum over here, n is equal to 0. Then we're going to have in the denominator is going to be n squared, then plus n, and then subtract 1/2. How do we actually approach this? Let's say we can actually unfoil this. Well, you can actually apply the quadratic formula for this, but I'm going to skip those, miscellaneous calculations. Well, it's not necessarily miscellaneous. This is just more tedious. We already know how to do quadratic formulas in that sense. So we have the infinite sum, n is equal to 0, and then after, of course, applying all that, quadratic formula, all that out, we'll have a factor of n plus 1 subtract the square root of 3 divided by 2, then multiply with n plus 1 plus the square root of 3 divided by 2. And then numerator still 1. So here's actually an identity we will be using. So this is, of course, part of the digamma function. And so the identity says that if we have the infinite sum from n is equal to 0 of 1 divided by n plus a and then times n plus b, then of course with digamma functions, that's the logarithmic derivative of the gamma function. Then of course this is actually valid for all numbers except at the negative integers and 0. So we have that this is actually the same thing as psi of a subtract psi of b, and then divided by a subtract b. And you can verify this yourself by using the limit definition. So it's the limit as n approaches infinity of ln of n, and then subtract that partial sum of, I believe it's 1 divided by z plus k. For in that situation, z is some sort of complex number. Then from here, you could actually just take that subtraction of psi of a and psi of b using that definition, and then of course doing algebra, and then we'll actually get that following identity just like that. So using this identity, so we can actually apply this to our infinite sum. So let's actually get to that. So now over here, we'll have that this is 1 plus 1/2, and then this is multiplied by psi of 1 subtract the square root of 3 divided by 2, then subtract, that's a multiply. I think I accidentally said subtract. Subtract this, subtract, then this is going to be 1 plus the square root of 3 divided by 2, all this being divided by, so now we're going to have 1 subtract the square root of 3 divided by 2, then subtract 1 plus the square root of 3 divided by 2. And so what we can do here is now using another following identity, we'll use that, this is known as the digamma reflection formula. So we have psi of 1 minus x, then subtract psi of x, that's going to equal to pi times arctangent, or not arc, just cotangent, pi times cotangent of pi times x. Okay, and so with this, we're actually going to apply that to that identity over here. So afterwards, we'll do this and say that this is 1/2, then multiply with psi of 1 subtract 1 plus the square root of 3 divided by 2. And of course, this is still psi of 1 plus the square root of 3 divided by 2. All this being divided by, so doing that subtraction, we'll get that this is the negative square root of 3. But then afterwards, after applying the pi, then cotangent identity, I'll actually distribute the negative back into here. So then this is going to become a 1 subtract 1/2, then multiply with pi times cotangent of pi times 1 plus the square root of 3 divided by 2, and then this being divided by the square root of 3. And so from here now, just doing a little more algebra. So this is going to be 1 subtract pi times 2 times the square root of 3, then cotangent of pi over 2, then subtract, or now this is actually add, my bad, plus pi times the square root of 3 and then divided by 2. And we can actually use a little symmetry identity to say that we can use cotangent of pi over 2 subtract theta, and then that's actually going to equal tangent of theta. So we can actually do this little replacement and say that now we have this as 1. Well, don't forget that this is actually now the input is supposed to be negative pi square root of 3 divided by 2 with a negative argument. That means that tangent is actually an odd function, so the negative has to come outside, meaning this will now change to a 1 plus pi divided by 2 times the square root of 3, then tangent of pi times the square root of 3 and then divided by 2. And so with that, that actually concludes, that's our S equals this evaluation over here. So I'll just actually, let me say that equals S, and then now we can actually just plug this back in. So now we're actually down to the final step. Now we can actually just combine everything together as 1. So now we're very close to finding what L is equal to our given sum. So this concludes that L is equal to 48, and then 48 is going to distribute this entire thing. So 48 and then plus 48 divided by 2 is 24. Then what I'll do after that is multiply the square root of 3 from both the numerator and denominator. And so don't forget there's a 12. So actually if I add that 12 back to the 48, so this is actually just putting everything together as 1. So this will become 60. And as I said, so this is going to now become plus 8 pi times the square root of 3 multiplied by tangent of pi times the square root of 3 divided by 2. And then close it off with, now we have 12 minus 12 Riemann zeta 2 or Basel's problems, and then zeta 2. So it'll become negative 24 times the zeta of 2. But we know that Basel's problem, that's pi squared divided by 6. Multiply that out. And so therefore with that comes down to minus 4 pi squared. And actually just like that, that is our final answer of what this infinite sum actually converges to. 60 plus 8 pi times the square root of 3 times tangent of pi times square root of 3 divided by 2, subtract with 4 pi squared. And just like that, that just completes it easily as that. So yeah, that's pretty cool if you ask me.